end the lesson on frequency analysis. In the last lesson, we saw examples of smoothing and sharpening filters. These are filters designed to suppress or enhance high-frequency content in a signal. More generally, how can we determine what is the frequency content of a signal? So far, we have just visualized the waveforms and inspected whether there were lots of oscillations. However, we have tools that let us quantify the power of different frequencies contained in a signal. The main tool for this frequency analysis is called the Fourier transform, named after French mathematician Fourier. Specifically for discrete time signals, such as those we represent in MATLAB, this is the discrete Fourier transform. This is implemented in MATLAB as the function IFFT, which stands for the fast Fourier transform. This function efficiently converts a time domain signal, that is, a signal that varies over time, into a frequency domain signal, that is, a signal that is represented not by how it changes over time, but by how much different frequencies contribute to the signal. This will not only let us easily see or quantify what frequencies exist in the signal, we can also very easily manipulate the frequency content of a signal in the frequency domain and then return the manipulated signal to the time domain form using the inverse Fourier transform, which is implemented as IFFT in MATLAB. Okay, let's go to MATLAB and see how this works. Let's start by creating a basic signal that is the sum of two cosines, as we have done before. We start by defining a sampling frequency, Fs, of 13,200 Hertz. The frequencies of our two cosines will be F1 equal to 440 Hertz and F2 equal to 660 Hertz. We'll make our signal 5 seconds long. We first define our time variable t to range from 0 in steps of 1 over Fs to time t minus 1 over Fs. Then we can define our cosine signals. First, y1, which is a cosine with frequency f1 equal to 440 Hertz. Then y2, which is a cosine with frequency 660 Hertz. We also add a phase to this cosine of pi over 4 radians so that we have a phase shifted 660 Hertz cosine. Finally, our combined signal is y is equal to y1 plus y2. So we know that for this signal we have a frequency content at 440 Hertz and at 660 Hertz. Thus, when we do frequency analysis on this signal, we should see power at these frequencies. Next, we plot our signals. We will ultimately have 9 plots that we want to show, so let's use a 3x3 grid of subplots. We'll show y1 in the first subplot, and we can zoom in on the first 10 oscillations of it using the axis function. Next, in a second subplot, we'll show y2, and zoom in on the first 15 oscillations of it. And finally, in a third subplot, we show the combined signal. And zoom in on the first 5 oscillations of it. We will not focus on this detail, but for those who are interested in the mathematics of periodic signals, we can note that the period of a signal, that is a combination of two periodic signals, is 1 divided by the largest common denominator of the frequencies of the two individual pure tone signals. Since y1 has a frequency of 440 and y2 has a frequency of 660, the largest common denominator is 220. 440 is 2 times 220 and 660 is 3 times 220. So when we combine the two signals into a combined signal y will be periodic with period 1 divided by 220. And to show 5 oscillations of y, we plot it from 0 to 5 divided by 220. Next, let's listen to our signals. We can first listen to the 440 Hz pure tone. Next, the higher frequency 660 Hz pure tone. And finally, the combined signal, which with a trained ear you may recognize as being the two tones played simultaneously. Next, let's compute our IFFT and look at the first 10 entries. Well, that's interesting. We can see in the first 10 entries of our IFFT, it looks like MATLAB prints 2 numbers for each entry, with the second number ending with the letter I. What's up with this? We can also see that MATLAB calls this data type complex double rather than just double. These are what are called complex numbers. We will dive into why we need complex numbers with the IFFT, but first, what are they? Complex numbers are different from real numbers. A full treatment of complex numbers is beyond the scope of this course, but a basic understanding is needed to understand why they are needed for signal analysis. One can consider real numbers to be one-dimensional. Real numbers increase from negative to positive values in one dimension on a line. Complex numbers, on the other hand, formulate a two-dimensional coordinate system where one axis is the real number line, and the other axis are so-called imaginary numbers. A complex number has two components, a real part and an imaginary part. We have the real number part of the complex number plane running from left to right, and the imaginary part of the complex number plane running from down to up. A complex number represented in so-called rectangular form looks like the format we saw in MATLAB. We state the value of the real part plus the value of the imaginary part multiplied by I, where I represents the square root of -1. Mathematically, the fact that I is the square root of -1 is of deep importance. But here, we don't need to worry too much about the math, and it is entirely sufficient to simply think of it here as an indicator to differentiate the imaginary part of the complex number from the real part. An example would be this complex number c. It falls at this location in the complex plane. Its position is defined by both its real part, which is x equals 0.9, and its imaginary part, which is y equals 0.5. So, c equals 0.9 plus 0.5i. In general, we can define any complex number c as being equal to x plus I times y, where x and y are any real numbers. For all complex numbers that fall on the real number axis, where y equals 0, this set of complex numbers are all perfectly real. So, real numbers are actually a subset of complex numbers that have an imaginary component that is equal to 0. We can similarly state that all complex numbers with real part x equal to 0 fall on our imaginary axis and are entirely imaginary numbers. And thus, purely imaginary numbers are also a subset of complex numbers. Okay, one more trick, and then we're ready to come back to the FFT in MATLAB. We've discussed representing complex numbers in this rectangular form, where we define c to be x plus I times y, but we can equivalently represent any complex number in a polar coordinate system. With polar coordinates, instead of using x and y, we define a 2D position by its displacement vector from the origin. More specifically, the length of the displacement vector, which is equal to the magnitude of the complex number, defines the distance from the point to the origin. And the angle the vector makes with the positive side of the real axis, called theta, these are the two quantities needed to define position in this 2D system. So here, if we know the length of vector c and its angle theta relative to the real axis, we know where it falls on our complex plane. Mathematically, we can go back and forth easily between these two representations. The length of the vector is the magnitude of the complex number, which is the square root of x squared plus y squared. Theta is the inverse tangent of y divided by x. In reverse, if we know the magnitude and angle, we can convert to x and y using the trigonometric sine and cosine functions. In the special case where the magnitude of the complex number is equal to 1, the length of the vector is equal to 1, and c falls a distance of 1 from the origin. This space of solutions, where magnitude of c equals 1 but theta can take any value, are said to fall on the unit circle, which is shown as the black circle here. On the unit circle, when theta is equal to 0, c equals 1 and is a real number. When theta is pi over 2 radians, c equals I. When theta is pi radians, c again is a real number equal to minus 1. At 3 pi over 2, c is minus I and purely imaginary again. Circling back to 2 pi, c again is equal to 1. Okay, so we have the basics about the general 2D nature of complex numbers. So now we can talk about why we need these 2D numbers with the Fourier transform. For the case of real-valued signals, which is where we will limit our scope, the Fourier transform tells us how to represent the signal as a sum of scaled cosine waves that oscillate at different frequencies. Each entry in our FFT corresponds to a specific frequency cosine wave. The complex number in that entry in our FFT needs to represent two quantities. One, the amplitude of a cosine that oscillates at that frequency, and two, the phase shift of the cosine that oscillates at that frequency. Ultimately, our signal can be represented by the sum of this set of cosines that are scaled and phase shifted according to the complex numbers provided by the FFT. As a result, the FFT also tells us about the frequency content of the signal. If the complex number in the FFT entry corresponding to a specific frequency has a small magnitude, that means that a cosine of that frequency doesn't contribute much to the overall signal, and thus that frequency is not present in the signal. On the other hand, entries in the FFT with large magnitude indicate a lot of power in the signal at that frequency. Here's a question. How many different cosines do we need to be able to represent a signal? As it turns out, this is a function of how many discrete time points we have in our signal y. Let's look at some small-scale examples to see why. These examples will also give us a tangible flavor of what the FFT is doing for us. First, we have a signal y that is equal to minus 1 at time 0 and 1 at time 1. We can easily define a cosine that passes through these two data points. Our FFT would tell us that for a cosine of frequency fs over 2 equals 1/2 hertz, we would multiply it with an amplitude of 1 and phase shift it by pi. The cosine itself is a continuous function. We can see that using half an oscillation of the cosine, phase shifted by pi, the value of this continuous function is equal to y at discrete times 0 and 1, where y is defined. In general, we can approximate any two data points with two cosines of specific frequencies. For two data points with sampling frequency fs equals 1 hertz, we can use one cosine with a frequency of 0 and another with frequency fs over 2 equals 1/2 hertz. The IFFT then finds the amplitude and phase that are needed to apply to these two cosines in order for their sum to pass through our signal samples. A cosine with 0 frequency is just a constant. So we can see our 0 hertz cosine is a flat line equal to 1. A cosine with frequency fs over 2 and amplitude 1 with 0 phase looks like our 1/2 hertz cosine. The IFFT tells us that we need 0 of cosine 1 plus 1 of cosine 2 phase shifted by pi in order to approximate this signal. The 0 frequency term captures the average value of our signal. Here, our y is equal to -1 and +1, so it has an average value of 0. But if instead y was equal to 0 and 2, our whole plot would shift up by 1, and we would want 1 of cosine 1 plus 1 of cosine 2 phase shifted by pi to approximate our signal y. Okay, let's add one more sample to y. Now we have 3 samples, and our y is equal to -1 at time 0, 1 at time 1, and 0 at time 2. We can still use just 2 cosines for 3 data points. The frequencies of our cosines are predetermined as a function of the number of data points and the sampling frequency of our signal. For 3 data points with fs equals 1 hertz, we will use a 0 hertz cosine and a 1/3 hertz cosine. The average value of our signal is still 0, so the IFFT tells us that in this case, again, we do not need any of the 0 hertz cosine in the IFFT cosine representation. However, for the 1/3 hertz cosine, we need a magnitude of 2 times square root of 3 over 3, and we need a phase shift of -pi/6. It is noteworthy that our IFFT cosine representation is defined by 3 numbers. The frequencies of the cosines, shown here in red, are predetermined by the sampling frequency and the number of data points in y. The actual values in y do not matter. No matter what values y takes on, they can be represented as the sum of cosines of those predetermined frequencies. Further, fs will change the frequency of the cosines, but not the number of cosines that are needed. The number of cosines is entirely a function of the number of data points. So for any 3 data point y, no matter what values it takes on, and no matter what the sampling frequency, we can always represent it as the sum of 2 cosines. The first cosine is always a 0 hertz cosine to represent the average value of the signal. For this term, there is no phase, as the phase shift of a 0 hertz cosine is meaningless. Then we have the magnitude and phase of our second cosine. So in total, our IFFT needs to compute 3 numbers to represent our signal as a sum of cosines. In summary, with y, we have 3 data points, and our IFFT needs to compute 3 unknowns. This should sound familiar from linear algebra. When solving a linear system of 3 equations and 3 unknowns, the linear system is fully determined and we can compute an exact answer. This is precisely what's going on here. We are in fact solving a linear system for the complex numbers used to define the amplitude and phase of cosine functions used to represent the signal. So this explains why a signal with 3 data points needs 2 cosines. With 2 cosines, we have 3 degrees of freedom in our cosine fit, with the amplitude of the 0 hertz cosine and the amplitude and phase of the second cosine. What happens when we add a 4th sample? Here we add a 4th sample at time 3 equal to 1/2. Now we have 4 samples that we need to represent as a sum of cosines. With only 2 cosines, and one of them being 0 hertz, we have only 3 degrees of freedom. So we need to add an extra cosine to bring our total to 3. With 3 cosines, we have up to 5 potential degrees of freedom. Carrying out this sequence to its logical conclusion, you can probably anticipate that for signals composed of n data points, we need n plus 2 divided by 2 cosines if n is even, and n plus 1 divided by 2 if n is odd. When n is equal to 4 and our sampling frequency is 1 hertz, our cosines have frequencies 0, 1/4 hertz, and 1/2 hertz. The FFT tells us that for such cosines, we can represent our signal with the following equation. As the signal becomes more complicated, so does our cosine representation. Again, the frequencies of the cosines in red are predetermined, but the FFT tells us the 5 numbers we need in green. We can continue growing our signal. With 5 data points, we end up with the result in green as a function of 3 cosines. Now here is a new signal y with 6 data points, but with values sampled from a normal random distribution. We need 4 cosines in this case, which becomes difficult to see if we continue to try to plot them here, so we just view the result. We could go arbitrarily high with this, but soon it gets too dense to plot. Here is a result with 50 data points in a normally distributed random valued signal y. As we can see, the FFT will always give us the right complex numbers to define the amplitudes and phases for a set of cosines to represent our signal. Let's go back to MATLAB and demonstrate the power of the FFT. Recall we have a signal y formed by the sum of a 440 Hz cosine and a phase-shifted 660 Hz cosine. Now let's compute the FFT. We will find it useful to write our own FFT function that performs 2 steps in addition to using the FFT function. Here's what I call my FFT function, which takes as input our signal y and the sampling frequency fs. The first thing we do is use MATLAB's FFT function to compute the standard FFT. Next, we can throw away part of the FFT result that we do not need. As we saw in the lecture slides, for a real-valued signal with n data points, we need the ceiling of n plus 1 divided by 2 cosines. But the FFT returns a result that has n data points. Why is that? The reason is that the FFT function works for both real-valued and complex-valued signal inputs. When the signal is complex, we have n complex values, which are 2 times n numbers, the n real plus n imaginary numbers that we need to approximate. That requires 2 times n degrees of freedom for our fits, which would require all n complex numbers in the FFT result. It also requires the use of complex waves instead of simple cosines. Since we will only discuss real-valued signals here, because this includes wide domains like sound signals, it turns out that if we limit ourselves to real-valued signals, we can throw away just about half of the FFT output without losing any information. In fact, we only need the first ceil of length of y plus 1 divided by 2 entries. The remaining part of the FFT that we throw away corresponds to what are called negative frequency components that we would need if we wanted to represent complex valued signals. Next, we can also compute the frequencies that each entry in the IFFT corresponds to. This is not something MATLAB gives us by default, but knowing these frequency numbers is useful. As we will see in the next section, the so-called Nyquist theorem tells us that if the sampling frequency of a discrete time signal is fs, the maximum frequency representable in that signal is fs divided by 2. Thus, the frequencies we can extract from our signal y range from 0 to fs divided by 2. The IFFT will assume we use cosines with uniformly spaced frequencies in this range. We define sampnum to be our sample numbers, which is a sequence of integers running from 0 to length YFFT minus 1. Then we can define our frequencies f as sampnum multiplied by fs over length y. Recall the units of fs is samples per second, in other words, hertz times samples. And length y is the number of samples, so we convert our sample numbers to hertz, which are our frequencies in f in hertz. And that's it. This code tells us the frequencies of the cosines in the range from 0 to fs over 2 hertz that can be summed to represent our signal. Next, we will also find it useful to write a plot function we will call magnitude spectrum plot, which will take as input our YFFT in frequency vectors. We'll have an optional third parameter for the color that's used in the plot. So, if the number of arguments input is less than 3, we will default our color parameter to B for blue. Then we plot the magnitude of the Fourier components as a function of frequency. We label the x-axis as showing frequency in hertz, and the y-axis is showing the magnitude of capital Y as a function of f, which is shorthand for the frequency components of little y of t. Okay, let's use our new functions. Recall our signal y is an audio signal that we can play with sound SC. The myFFT function lets us compute our YFFT in frequency vector f. And we can plot the result in another subplot. We use our magnitude spectrum plot function with inputs YFFT and f. And we can give it a title, magnitude spectrum. We can see that our plot function has plotted the magnitude spectrum, which shows the Fourier components to all be zero, except for at two frequencies, which correspond to 440 Hz and 660 Hz. The magnitude of the Fourier components are zero everywhere except for these two frequencies. For example, looking at the first 10 components, we see that we get numbers with magnitude on the order of 10 to the minus 9, which are consistent with floating point round-off errors. Looking at the 440 Hz component, we see it has a magnitude of 33,000 in the real part. When we look at the length of y divided by 2, we see that that is equal to the magnitude of our Fourier component. So we can see when we divide the magnitude of our Fourier component by length of y over 2, we arrive at 1, which is the amplitude of the 440 Hz cosine component of the signal. Similarly, when we look at the magnitude of the 660 Hz component, we also see that it's equal to 33,000, and thus if we divide this by the length of y over 2, we also arrive at 1, which is the amplitude of the 660 Hz component. Although this Fourier component has a non-zero phase, that is, when we look at both the real part and the imaginary part, we see they're both non-zero. Using the angle function, we can see that the angle of this component is pi over 4, corresponding to the phase of the 660 Hz cosine that we created. So in summary, we have confirmed that we can use the IFFT to extract the power of specific frequency content in a signal and the phase angle of those frequencies needed to reconstruct the signal. Next, let's demonstrate how to do this. We're going to demonstrate how to use the Fourier transform to reconstruct a signal as a sum of cosines. Let's start with a more complicated signal than a sum of two pure tones. Let's load a speech audio sample from MATLAB. This loads into 5 seconds of a speech signal, and we can create our time-independent variable as ranging from time 0 in steps of 1 divided by fs to length of y minus 1 divided by fs. Playing it, we can hear it is a speech segment regarding the Fourier transform.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Can also plot it. And also plot the Fourier transform magnitude spectrum plot. We can see this is a much more complex signal than the two pure tones signal we saw before, and thus we have non-negligible power in frequencies across the whole spectrum. We are going to display our reconstruction of the signal from cosines progressively in the second subplot. We start with zeros in a vector called y cos. Then we define a for loop to loop over the frequencies we have in IFFT. To progressively add in each iteration to y cos the magnitude of the FFT for the ith frequency divided by the length of the signal y to scale a cosine with frequency f at I plus phase equal to the angle of the FFT at the ith frequency. So this is a cosine of frequency f at I with its amplitude and phase determined by the FFT. Next, we need to put this into an if statement because we need to do things slightly differently for frequencies 0 or fs over 2. So when I is equal to 1, we have our 0 hertz component, or in the last iteration, if the frequency is exactly equal to fs over 2, then this is the correct code. Otherwise, if we are at other frequencies between 0 and fs over 2, we need to have the length of y so that we're dividing by length of y divided by 2, effectively doubling the magnitude. That's it. So this for loop will reconstruct our signal y as a sum of cosines using the FFT result. We can verify that y is equal to y cos by taking the sum of the squared differences between the two. And we see the differences between y and y cos are minuscule and consistent with tiny floating point precision errors. Okay, let's run that for loop again, but this time let's add plotting and audio code to visualize and hear the quality of our cosine approximation as we progressively add higher and higher frequency content to our signal. So within our for loop, we're going to add another if statement. That will update the plot every 100th iteration. So if the modulus of I after dividing by 100 is equal to 0, then I is a multiple of 100, and we will plot our signal y cos. We can give it a title. This is an approximation of y of t as sum of I cosines with magnitude determined by the magnitude of the Fourier transform and phase determined by the angle of the Fourier transform. This is in a loop, so we need to use draw now to request MATLAB to stop and redraw the figure before proceeding to the next iteration. Then we close our for loop and run it. We can see as we add higher and higher frequency content to our cosine approximation of our signal IFFT, the signal appears to get closer and closer to the shape of signal IFFT. There are still a few spots where some of the higher frequency content has not quite been recovered. But as we can see from our magnitude spectrum plot, there's a broad range of higher frequencies that contribute some to the overall signal, but have relatively little energy compared to the lower frequencies. And we can see the final result plot of y cos is identical to y. Next, let's run it again, but with audio to hear what the approximation sounds like. Let's also pause less frequently, say at 4 time points. Once we reach 500 hertz, 1500 hertz, 2500 hertz, and 3500 hertz. So we start with a new variable, f break, which we'll set to be 500 for stopping at 500 hertz. We reset y cos to be zeros and repeat our for loop. And now, instead of stopping every 100 iterations, we'll stop whenever our frequency, f at I, becomes greater than f break. And we repeat our plotting code. And we also add to the third subplot a red line at the frequency where we're breaking. This will be a vertical red line at x location f at I, with height ranging from 0 to 600. And we can play our audio approximation using the sound.sc function. We include pause so that the code will pause at this point until the user hits enter on the keyboard. And to wrap things up, we also change the value of f-break by adding 1,000 to it. So the first time this if statement is executed is when the frequencies in f at I become greater than 500 hertz, because that's our original value for f-break. And by incrementing it by 1,000, now this if statement will execute again whenever our frequencies f at I become greater than 1,500 hertz. And then we'll iterate by another 1,000 hertz, increase by another 1,000 hertz. So then we'll stop again at 2,500 and then again at 3,500 hertz.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Okay, so when we run it, we pause after 500 hertz have been included, which amounts to 2,497 cosines. We heard the muffled sounding version of the audio signal. That muffled quality is what results when we remove all frequencies higher than 500 hertz. And only keep frequencies lower than 500 hertz in our signal. From afar, our y cos signal already looks much like the signal y in our plot. But if we zoom in on a section, we can see differences. While the overall shape in y cos generally looks similar, we can see that much of the quickly changing high frequency content that exists in y does not exist in y cos. Okay, we can hit enter now and continue on.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Next, we have y cos as a sum of 7,487 cosines to reconstruct our signal with frequencies up to 1,500 hertz. That already sounds much less muddled, and we are still ignoring all frequencies from 1,500 to 4,000 hertz. Going again.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Now we add frequencies up to 2,500 hertz with 12,477 cosines. And that signal sounds almost as good as the real one. In the power spectrum, it does not look like much is going on in this region, but if we zoom in, we can see there is a low level of power coming from frequencies in this band that is still needed to accurately represent the sound signal.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
We can appreciate that as we add in our high frequency content, we ultimately fully reconstruct our signal from individual frequency components. This demonstration reveals two important concepts. First, it shows that the IFFT provides us the information needed to define the magnitude and phase of each cosine used to represent the signal as a sum of cosines. We showed that by summing cosines using the IFFT, we can reconstruct the signal. But more importantly, we can detect the amount of power in a signal in different frequency bands and display it as the magnitude spectrum for the signal. This is arguably the most fundamental of all signal analysis tasks. And not only can we detect it, we can easily manipulate our signal by picking and choosing the frequencies we want. We can boost the power in some frequencies and diminish it in others, or we can remove all power from specific frequency bands. This is the process called filtering. For example, we can define a high-pass filter that will let all frequencies greater than 1500 Hz remain in the signal, while removing all other frequencies. It is called a high-pass filter because it is designed to let all the high frequencies pass through it while filtering out frequencies lower than 1500 Hz. This filter H is equal to 1 for all frequencies greater than 1500 Hz and equal to 0 otherwise. To apply the filter, we simply do an element-wise multiplication of the FFT of the signal with the filter. This gives us the Fourier transform of the filtered result, where the amplitudes of the cosines we would use to reconstruct the function that have frequencies less than 1500 Hz have been zeroed out. We can plot the spectrum of this new signal on top of the old one in red. As you can see in the plot, we simply delete all of the lower frequency portion of the spectrum. And what we have left is the remaining portion in red. So, how would we reconstruct this high-pass filtered signal? Well, we could use a for loop, as we did above, and sum together all the cosines one by one, but this is really inefficient. It is much faster to use MATLAB's IFFT function, or inverse fast Fourier transform function, to inverse the frequency domain representation back to a time domain representation. We'll create a myFFT function. My IFFT function will look like this. We'll take as input the Fourier transform, our frequency vector, and sampling frequency fs. We need an if statement to properly rebuild the portion of the FFT that we threw away in our myFFT function. If our FFT does contain frequency fs over 2, then our full FFT for signal y can be reconstructed by computing the IFFT of YFFT followed by the complex conjugate of reversed entries in YFFT from 2 to n minus 1. Corresponding to the frequencies between 0 and fs over 2 Hz. We need to reverse this vector using the flip up-down and append it to the end of the vector. Then we can just use MATLAB's IFFT function to compute the time domain signal y. Else, if we don't have frequency fs over 2, we do exactly the same thing but for entries 2 to end of our YFFT array, since there is no entry at the end for frequency fs over 2. What we are doing is ensuring that the FFT we input into MATLAB's IFFT function is, quote, conjugate symmetric. As the speech in the audio file says, the Fourier transform of a real-valued signal is conjugate symmetric. That is, the tail of the Fourier transform is the mirrored complex conjugate of the front of the Fourier transform for real-valued signals. So for real-valued signals, these entries provide no additional information. The only reason these components are ever needed is in case y is a complex rather than a real-valued signal. In that case, these components are not generally equal to the complex conjugate of the first components. This situation involves mathematics that are beyond the scope of this course. For our purposes, we can just ensure our MATLAB and IFFT functions are exactly as demonstrated, and they'll work for any real-valued signal. With our function in place, our filtered output signal, y high pass, can be found with one simple line of code. Using our IFFT function. Then we can plot it. And we can see that it does look quite different from y of t. We can also listen to it.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Listening to it, we can hear that it is absent of lower pitched tones, and only the high frequency content remains. Of course, this can be repeated for a low-pass filter, where we let low frequencies pass through the filter, but filter out high frequencies. This is a low-pass filter at 500 hertz. We can see in green where we are retaining all of the information below 500 hertz and throwing the rest of it away. Our y low pass is the IFFT of the results. And we can listen to it.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
When we remove all frequencies beyond 500 hertz, we get that muffled quality where all the high-pitched tones have been removed. And we could pick out a different frequency band to keep. Instead of having a high pass or a low pass filter, we could have a so-called band pass filter, where we keep frequencies greater than 500 and less than 1500. Again, we filter our signal in exactly the same way. And we can show the magnitude spectrum in magenta. And we can see in our magnitude spectrum plot this signal has frequencies between 500 and 1500 hertz. Outside of that, all of the energy has been zeroed out. Our Y bandpass is the same as the Y low pass. We compute the IFFT of our filtered result. We can see it also looks quite different from our original signal y of t. And we can listen to it.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
And we hear a very different result with the bandpass signal. Next, let's look at an example with filtering a noisy signal rather than a clean signal. We read in a noisy signal. And we can listen to it.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
We hear that it is indeed very noisy. Next, we find the Fourier transform. And plot the magnitude spectrum. We see lots of power exists in the high frequency content of the signal, which is where most of our noise is located. So we should try a low pass filter. Let's try eliminating frequencies greater than 1500 hertz. We can see in our plot that in our filtered result, the spectrum has zeroed out all information beyond 1500 hertz frequencies. Now let's listen to it.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Compared to our original signal, much of the noise has been eliminated. The trade-off is that we have also removed some high-frequency content from the signal itself, so the speech does not sound as sharp. Noise reduction is always a trade-off between how much noise can be removed without affecting the quality of the signal too much. Thus far, we have looked at what are called ideal or square wave frequency filters. Square wave filters keep the entirety of the desired frequencies and completely remove the undesired ones. Often, smoother transition filters are used and have more desirable mathematical and practical properties than so-called ideal filters. For example, one of the most common filters is a Gaussian filter. Gaussians have many mathematical properties that make them desirable as signal processing filters. Let's compare the Gaussian and square wave filter. In a new figure, we will have frequency on the x-axis and filter magnitude on the y-axis. And we can plot our square wave filter. We will do so in this plot by mirroring the frequencies across the origin. Visualizing both negative and positive frequencies is another common approach for visualizing frequency spectra. But the magnitude spectra are always mirrored about the origin for real-valued signals, like the ones that we deal with. However, momentarily switching to this visualization approach will help us appreciate why our filters are called square wave and Gaussian filters. So we plot with frequency values that are mirrored about the origin using the minus flip-up-down function, followed by the positive frequencies. Then we set the y values using the same mirroring approach. For our filter H. Missed a semicolon. Now we can instantly see why this is termed a square wave filter. In the frequency spectrum, takes the form of a square wave that rises discontinuously to 1 and falls back down to 0 for a specific band of low frequencies less than 1500 hertz. Next, a comparable Gaussian filter. We set the sigma for the Gaussian to be equal to 1500 for 1500 hertz. Let's also define a signed frequency variable, SF, using our negative and positive frequencies. Then we can plot, as a function of our signed frequencies, our Gaussian. The Gaussian function is the natural exponent raised to the power of minus our signed frequencies squared divided by 2 times our sigma squared. There is also traditionally a scaling factor used to normalize the integral of the Gaussian function. However, this is often ignored for signal processing applications because it is often more convenient to retain the maximum value of 1 where the argument of the exponent is 0. That's when our frequency f is equal to 0, and have it have values that diminish from 1 towards 0 for greater deviations from the 0 frequency. And we can add a legend. So the Gaussian shape, the normal distribution bell curve, is unmistakable. The so-called bell curve has a maximum height of 1 where f is equal to 0, then smoothly decreases towards 0 as we move away from the 0 frequency. The point of steepest descent is where f is equal to sigma, which in this case is 1500. This is why we choose the sigma for the Gaussian as our cutoff frequency. Using this smoothly sloping frequency suppression function as opposed to the square wave filter can often produce better results with fewer artifacts. Okay, let's try it out. Here's our Gaussian filter, H. With G sigma equal to 1500 hertz. Can apply it to our signal. And let's take a look at the results in a plot. We'll plot the Gaussian filter results in green. So we can see in the power spectrum we never really dropped to 0, but beyond 1500 hertz the power in these frequencies is quickly suppressed to very small magnitudes. And we use the IFFT function to reconstruct the filtered results. Now let's compare how these three signals sound. First, the original very noisy signal. And when we play this signal, pay attention to the S sounds that are the high frequency parts of the speech that cut through the noise.
The discrete Fourier transform of a real valued signal is conjugate symmetric.
Now the YLP, which was created using the ideal square wave filter, again pay attention to the S sounds.
The discrete Fourier transform of a real valued signal is conjugate symmetric.
You can hear the noise has been reduced, but those S sounds have almost entirely been eliminated. Now our Gaussian low pass.
The discrete Fourier transform of a real valued signal is conjugate symmetric.
We get almost as good noise reduction, but the speech still sounds clear and the S sounds are retained when we use the Gaussian rather than the ideal filter. Next, let's look at something that's not speech, but rather music. Let's load our rock guitar sample. And add our distortion effect. Where we clip the maximum value of our signal. And we're actually clipping the magnitude of the signal so that the positive numbers can be no greater than max and the negative numbers can be no less than minus max. We'll listen to a portion of it. This tends to create a lot of power in high frequencies due to the introduction of the very sharp changes to the signal that we create when we clip it, and it also tends to suppress lower frequencies. So we can see this if we look at magnitude spectrum plots. Zooming in, we can see we've reduced our low frequency content in our red signal. And in the high frequency region, our new signal has much more content. So we can try to clean this up a bit by doing some low pass filtering and low frequency amplification. So let's create a Gaussian filter with a sigma equal to 3000. And we multiply it by 5 so that the filter actually amplifies the low frequency content. We've amplified our low frequencies to about the same level that they were originally. And zooming in, we can see suppression of the high frequency content. We again use our IFFT function to reconstruct the result. And we can listen to it. First, our original signal. Then the raw distortion result. And now distortion with boosting of the low frequencies. If listening with a sound system that has decent low and high frequency response, a trained ear can hear we have a fuller sounding signal without so much high frequency fuzz. There are many other frequency filter design tools available in MATLAB that could assist with designing filters that can be built in the real world using circuits, for example. For example, we saw the use of finite impulse response filters in a previous lesson. However, direct manipulation of the spectrum using the Fourier transform is the most versatile method for manipulating frequency content. MATLAB also provides some built-in tools for analyzing how frequencies in a signal change over time. For example, in our guitar signal, sometimes low-pitch single strings are strummed, generating relatively low frequency content, and other times all strings are strummed, generating broad spectrum power in the signal. Let's first load the 44.1 kilohertz version of our guitar signal. And we can listen to the first 4 seconds of it. Listening to the first 4 seconds, we hear 3 broad strums interleaved by single string plucks. So, how can we use MATLAB to analyze how the frequency content changes over time? Spectrograms are plots that do exactly this. In order to analyze frequency as a function of time, we have to consider windows of time. Within a time window, the spectrogram will use the IFFT to analyze the frequency content, then do the same for the next time window and the next, and so on. These time windows can overlap, and there are many options that can be determined for how the windows should overlap. These choices are all application dependent and could require some tuning to get right. Here we'll leave most of this at the default values, but we will choose what is often the most important parameter, the window size. We choose the window size to be 1024 samples, where with a sampling rate of fs equals to 44.1 kilohertz, this gives us a time window of approximately 25 milliseconds. We leave the next parameters at default with square brackets. Then we tell the function our sampling frequency. Okay, so what are our outputs? We see S is a matrix that's 513 rows by 343 columns. F is a 513 by 1 vector containing the frequencies of the Fourier transform. T is a 1 by 343 vector containing the times at which a window of the signal was sampled and a Fourier transform was computed. S contains the Fourier transform complex coefficients that result. Each column of S is a 513 row by 1 vector corresponding to the FFT of the signal in that time window corresponding to that column. So, in this matrix we have 343 different Fourier transforms that have been performed on small subcomponents of the signal. We can inspect a few of the Fourier coefficients in the first 4 rows and 4 columns of the matrix S. So what's a better way to display the results? We can't display them the same way we did with our magnitude spectrum plots. There we had a single spectrum. Here we have 343. So plotting them the same way would make interpretation impossible. But 2D data we can display as an image. So, to display the result, we'll use the image SC function, which can display an image in a figure window. We'll see more about image display in the following lesson on image analysis with MATLAB. We provide image SC with the x-axis coordinates of each column of the matrix to be displayed as an image using the frequency vector f. The y-axis coordinates of each row of the matrix to be displayed using the time vector t. And then similarly to the magnitude spectrum plots that we've done, we want to display the magnitude of the FFT components. Here we transpose S so that the frequency dimension is on the columns and the time dimension is on the rows. And we take the logarithm of the magnitude of the Fourier coefficients to heighten the smaller magnitude content. Color bar provides a legend that tells us how the numbers in the matrix being displayed are translated into the colors assigned to the display pixels. Axis XY makes the y-axis point up in the direction that time increases. And finally, we can label our axes. We have frequency in hertz on the x-axis, we have time in seconds on the y-axis. So going from down to up, we move forward in time in our 4-second signal. On the x-axis, we have frequency in hertz, increasing from left to right. At every xy location in our plot, a color is shown indicating the magnitude of the IFFT coefficient. So what is shown is the magnitude of the frequency content for each frequency in the signal on the x-axis as a function of time on the y-axis. Each horizontal line in the plot corresponds to one 25 millisecond time window, where colors shown on that horizontal line are akin to the height of our 2D magnitude spectrum plots. So instead of having one magnitude spectrum plot for the entire signal, the spectrogram generates individual plots for small time windows. Does the content make sense? It looks like at time 0, not much is going on. This is before the guitar is being played. Then we see some low frequency energy around time 0.25 as strings are being plucked. Then around time 0.75, we see broad spectrum power to high frequencies that tapers down over time. This is when all the strings on the guitar are being strummed, and that strummed note is being held momentarily. We again pluck some lower frequency notes around time 2.25, then have another strum at time 2.75, and again at time 3.75. The spectrogram contains a very useful visual representation of how frequency content in the signal changes over time. Let's listen to the sound again with the spectrogram displayed. And while we play the sound, we can also draw a line on our spectrogram corresponding to the passage of time. We start with this if1 statement, and so we're going to wrap all of our code in this if statement so that it doesn't execute until we end the if statement. Sound SC will kick off our sound. But not immediately. On my MATLAB Online, I find I need to pause for about 0.35 seconds for the sound to actually start playing. At this point, we wish to begin showing our line. Tick starts the clock at time 0. And we will keep drawing the figure in a while loop for 4 seconds. So we use a while loop that stops when our time tm becomes larger than 4. We hold off to permit redrawing the figure. Then we repeat our spectrogram plot identically to above. Finally, we want to draw our line indicating the current time in the signal. We get the current time using the talk command. Then we can plot a horizontal line across all frequencies in the figure from 0 to fs over 2 at time tm. We do a draw now to make MATLAB plot it immediately. Okay, let's execute it. Listening to the sound with the spectrogram, we can see the spectrogram contains lots of useful information about how the signal frequency content changes over time. We can appreciate the sharp, broad spectrum energy in the signal created by a quick strum of the guitar strings. We can see how the strength of the strum signal tapers off over time as the guitarist holds the note with the high frequencies tapering off more quickly. The shape of the spectrum changes as different individual strings are plucked. To summarize, Frequency analysis is an extremely powerful way to analyze the frequency content and manipulate a wide variety of signals. We've focused here on sound signals as they are easy to plot and listen to, but these same analysis methods are widely applicable. For example, the same tools are used for analyzing the radio spectrum in radio astronomy, or more generally, any type of data that is time varying.